Hello and welcome to the Stoichiometry unit. Stoichiometry, it's a great word, isn't it? Let's learn what that means. So if you were with us when we were talking about the mole, we started out that unit by saying everything around you is made of chemicals, and a lot of those things are made by people. In order to make things, if you want to make them economically and efficiently with as little waste as possible, as little cost as possible, knowing exactly how much to start with and how much you're going to end up with, there's got to be a way of calculating all of that. And that's what stoichiometry is all about. The quantitative study of chemical reactions is called stoichiometry. So, if you watch this video and do the practice problems and make a little bit of effort, you should be able to calculate the amount of reactants required and or products formed in a chemical reaction. And you should be able to do that in terms of moles, mass, which usually we measure in grams, and volume, which usually we are going to use liters. It's the mole concept that allows us to do these calculations. Everything must go through moles is one of our sayings. So if you're one of Dr. Kemp's students, make sure you have your mole roadmap handy, our conversion chart that tells us which factors to use as we're going through a mole conversion. So imagine that you want to manufacture table salt from its component elements. You may have heard that table salt is sodium chloride, so we would need some sodium and some chlorine. The balanced chemical equation then would be what's shown on the screen. 2 sodium atoms, 1 chlorine molecule would make 2 sodium chloride formula units. But as we learned in the mole unit, we can look at this as a mole ratio. So it's a 2 to 1 to 2 ratio of atoms in order to get the product. So if we look at this in terms of molecules, we can read it one way, but we can also read it in terms of moles. We can look at those coefficients as our mole ratios. If you read this equation as a mole ratio, you might say 2 moles of sodium, 1 mole of chlorine. But you don't have to start with a whole mole of chlorine. The mole is a number. You can have any part of a mole or any multiple of a mole. What if you started with 10 moles? If you started with 10 moles of chlorine, how much sodium would you need? The ratio is 2 to 1. So if you started with 10 moles of chlorine, you would need twice as much, or 20 moles of sodium. By any other factor, you can figure out that if you start with, say, 10 moles of sodium and you have as much chlorine as you like, then you could figure out how much sodium chloride you produce. Can you do that? 10 moles of sodium would make how much sodium chloride? Well, look, it's a 2 to 2 ratio, which is the same thing as a 1 to 1 ratio. In other words, however much sodium you start with, that's how much sodium chloride you'll end up with, assuming you have enough chlorine to make that much. So if you start with 10 moles of sodium, you'll produce 10 moles of sodium chloride. So let's look at this problem-solving process a little bit more formally. Here's the problem again. If you start with 10 moles of sodium, how much sodium chloride can you produce, assuming chlorine is in sufficient supply? Let's follow our problem-solving process where we are going to write what we're given way over on the left side of our page. So we'll say 10 moles of sodium. We'll write what we want to find way over on the right side. We want to find moles of sodium chloride. And so what we need in between is a conversion factor. We need something that is equivalent to 1 that will change from moles of sodium to moles of sodium chloride. And where that comes from is the balanced chemical equation. The mole ratio, 2 moles of sodium to 2 moles of sodium chloride, can be a conversion factor. We'll put the 2 moles of sodium on the bottom of the fraction so that when we multiply 10 moles of sodium in the numerator of the other fraction, those moles of sodium will cancel out. We can just mark right through them. That leaves us with 10 times 2 moles sodium chloride over 2. And of course that equals 10. 2 over 2 is 1. 10 times 1 is 10. So the answer is 10 moles of sodium chloride. So if all we ever had to deal with were whole moles, 2s and 3s and 4s and 5s, then stoichiometry really wouldn't be that difficult. But you don't have to have a whole mole. The mole is just a group designation for Avogadro's number. So you can use any amount of that you want to, or you can use multiples of it. So for example, if we were making sodium chloride and we always had to use whole moles, then we would always end up with 116.89 grams of sodium chloride, and that's ridiculous. What if we didn't want 116.89 grams? What if we wanted 1,000 grams or only 5 grams? There's got to be a way to calculate that. And of course, that's where stoichiometry comes in. You do have to use whole atoms or whole molecules to react, but you don't have to use whole moles. You can have any part of a mole you like, as long as you use the correct ratios, which are given by that balanced chemical equation. So for example, let's say you want to know the mass of water you can produce with 7 grams of hydrogen, assuming you have as much oxygen as you'd like. First, you must always start a stoichiometry problem with a balanced chemical equation. Not just any old equation, it has to be balanced so that you have the mole ratio. So the balanced equation for the manufacture of water is 2 molecules of hydrogen, 1 molecule of oxygen will produce 2 molecules of water. So we'll now follow a series of steps to answer our question, how much water can you produce starting with 7 grams of hydrogen? So our general procedure goes like this. If I were you, I would not skip this first step. You have to start with a balanced chemical equation, and the very next thing I would do is list what you are given right next to that equation, and list what you want to find right next to that equation. Put an amount for the given and the units that you're starting with. For the unknown, put the units that you desire. Now, it's a good idea to draw a line through any other substances that are not relevant to your problem. You need them to balance the equation, but you do not need them in order to solve the rest of this problem. So if I were you, I'd mark through them so that you don't focus on them. Solving problems like this is going to require several steps, and the mole roadmap can help us out. We are starting down on the lower left where it says mass, and we also want to end up on the lower left where it says mass. The difference between this and the earlier problems that we worked out in mole conversions is that we were using the same substance, so we would go from grams to moles or from moles to grams, one way or the other. In this case, we're going to change from grams of one substance to the grams of a different substance by going through the moles. So you have to do a conversion from mass to moles, do a mole exchange, and then go back to mass. But as you go back, you have a different substance. So if I were you, I would set my problem up in a grid like the one shown on the screen. What you are actually going to do is a series of multiplications of different fractions, but to consolidate the space and keep it a little more organized, I like to put it in a grid. So in the first box of the grid, you write what you are given. Write a number, a unit of measurement, and the substance's formula. Number, unit, substance. We are given 7 grams of hydrogen. Over on the right-hand side, you should list what you want to find. So we want to find grams of water. We don't know the number yet, that's our unknown, but go ahead and write the units and the substance. Now what goes in the grid where it says step 2, step 3, and step 4 are conversion factors, fractions that are equivalent to 1, and we can figure out which goes in which box by looking at the mole roadmap. So if you get your mole roadmap out, and you start with grams and you want to go to moles, it says that what you should do is multiply by the molar mass on bottom and 1 mole on top. The mole roadmap is generic. We have to supply the specific information. So what we want to find is the molar mass of hydrogen. H by itself is 1.01, so times 2 is 2.02 grams of H2. That's equivalent to 1 mole of H2. Now the grams in the numerator under step 1 and the grams under step 2 are both of hydrogen, and so they are going to cancel each other out. We can go ahead and mark through them. It leaves us with moles of hydrogen, which is a fine thing to have, but it is not the substance that we want. So where it says step 3, that's where we are going to use the balanced chemical equation. In step 3, you look at your balanced chemical equation and you just basically insert the word mole between the coefficient and the substance. So we have 2 moles of hydrogen for every 2 moles of water produced. Notice that I put the moles of hydrogen in the denominator, and that way it will cancel the moles of hydrogen in the numerator of the previous step. This is the only step where we use the coefficients. In step 2, we wrote 1 mole. That's because we are simply doing an equivalence. We want how much 1 mole weighs. In step 4, we will also use 1 mole because, again, all we want is an equivalence. But in this case, in step 3, what we did was we exchanged moles. We went from moles of hydrogen to moles of water. Now we have the right substance, we just don't have the right units. So we're going to do one more step. In step 4, the mole roadmap tells us to convert from moles to grams. We have to put 1 mole on bottom and molar mass on top. In this problem, you have to supply the specific information. So you put 1 mole of water and you put the molar mass of water, which is around 18 grams. Now all we have to do is cancel out our moles of water on top and bottom and do a little math. The 2's in step 3 are both going to cancel, so it will be 7 times 18.02 over 2.02. And the only units we have left are grams, and the substance we have left is water, which is exactly what we want to find. So 7 times 18 divided by 2 is around 62.45. All right, so we were able to figure out, given a starting amount of a substance, how much of another substance we could produce. Let's try another example. How many grams of sulfuric acid are required to react completely with 15 grams of zinc in a single replacement reaction? You'll notice that you are not given a balanced chemical equation, and so we have to actually go and make one up before we start on the stoichiometry part. So you should recognize that sulfuric acid, being an acid, is something that you can look up if you don't already remember that it's H2SO4. Zinc is just an element and it's Zn, and since they are reacting together, we write both the zinc and the sulfuric acid on the left side of an arrow. Now, we are not told what the products are, but we are given a clue. It tells us that it is a single replacement reaction. That means the zinc will swap places with one of the elements in the sulfuric acid. Like replaces like, so zinc is going to become a positive ion. It will replace the positive ion in the sulfuric acid, and the positive ion is the H. So zinc and H will trade places. We will get zinc sulfate and hydrogen. But this is not time to start balancing because we have to check whether or not these products we have predicted have the correct formulas. Now it turns out that zinc is a positive 2 and sulfate is a -2, and so that's okay as an equation, but the H is not okay. Hydrogen is diatomic in nature. It will always bond to something, and if nothing else is around, it bonds to itself. So we don't ever write H by itself. It should be H2. Now, since none of the subscripts changed, we won't need any coefficients. This equation is balanced. As I told you before, this is an important step. If I were you, I would now write what I'm given somewhere close to the equation. We have 15 grams of zinc. I would write what I want to find, which is an amount of sulfuric acid. You'll notice that this problem is different from our first problem, where we had a given amount of a reactant and we were asked to find an amount of product. In this case, both our known and our unknown are parts of the reactants. Since we don't need the products after we balance the equation, if I were you, I would mark through them. So we are given zinc. We want to find how much sulfuric acid we are going to need, and we don't need to know anything about zinc sulfate or hydrogen gas for this particular problem. The mole ratio is a 1:1. So if we go through our steps for solving mass-mass problems, we will make a grid. Make your grid. Write what you know in the upper left-hand corner, 15 grams of zinc. I left off a 0 or 2 there on the PowerPoint that I'm making. If I put too many numbers in these boxes, they get too small to see. Way over on the right-hand side, we have grams of sulfuric acid. That's our unknown. We need a series of conversion factors. We're going from a mass of one substance to the mass of another substance. So just like last time, we're starting in the lower left-hand corner of our mole roadmap, and we're going up toward moles. The mole roadmap tells us to put molar mass on bottom and 1 mole on top. We have to supply the specific information. We want the molar mass of zinc and 1 mole of zinc. 1 mole of zinc on top and the molar mass of zinc on bottom. The molar mass of zinc is around 65.4 grams. Now the grams of zinc on top and bottom will cancel each other. So those cancel out and they leave us with moles of zinc. We want grams of a different substance. We have to keep going. We're at moles, and this is where we do our mole exchange. In this particular problem, it's a 1:1 ratio. So we just have to make sure we write them in the right boxes. The zinc is going to be on bottom because we're trying to get rid of zinc on top. We want zinc in bottom, and we want to change that to sulfuric acid. So I'll write a 1:1 ratio in the third column. The moles of zinc are going to cancel out. And now you are going to have moles of sulfuric acid. We want grams. We have to do one more conversion. To get from moles to grams, the mole roadmap tells us to write 1 mole in bottom, molar mass on top. The molar mass of sulfuric acid is around 98 grams. So I put 98.1 on the screen. 1 mole of sulfuric acid on the bottom. The mole of sulfuric acid on the numerator and denominator will cancel each other out. We are left with 15 times 1 times 1 times 98.1 grams of sulfuric acid. And then in our denominator, we have 65.4 times 1 times 1. If you do the math, you'll get 22.5 grams of sulfuric acid. So that's our final answer. It always helps the teacher if you write that out very clearly, maybe circle it like I did on the screen, or write it out separately. My answer is 22.5 grams of sulfuric acid are needed to react to 15 grams of zinc. One of the biggest mistakes that I see chemistry students make is they rush through these problems and they don't write everything down. Please slow down. Slow down and write it down to get it right. Write it down to get it right. In every box, write a number, a unit of measurement, and the substance. Then you can follow along as you go with cancellations of the units and the substances to make sure that you're on the right track. Let's do one more example in this video. Let's determine the number of grams of ammonia. Ammonia's formula is NH3. How much ammonia is produced by the reaction of 5.4 grams of hydrogen with an excess of nitrogen? Anytime you see that word excess, it means that you have as much of that substance as you want. It will not limit your production. So we can basically, after we balance the equation, we can ignore nitrogen. But we are going to need it to balance our equation, and we need to write its formula correctly. So we know that nitrogen and hydrogen are going to form ammonia. Would this be the correct start of our equation? Well, it might make a great start, but it's not complete, because nitrogen and hydrogen are 2 out of our 7 diatomic elements. It would be really helpful if you would memorize all 7 of them. So we should write N2 and H2. Now, are we ready to draw our grid? No, because our equation must be balanced. This is not a balanced equation. We have the wrong number of nitrogens and hydrogens on the left and right. They don't match up. So we're going to need a coefficient of 3 in front of the hydrogen and a coefficient of 2 in front of the ammonia in order to get this equation to balance. Now we have a balanced chemical equation. Now we can draw our grid and get started with the stoichiometry. First, as I've said before, it would be a good idea to label our equation with our given and our unknown. We are given 5.4 grams of hydrogen. Our unknown is a quantity, a mass of ammonia, and we have an excess of nitrogen. Anytime it says excess, that's the one you want to mark through. So in our grid, we're going to write 5.4 grams of hydrogen over on the left-hand side, grams of ammonia way over on the right-hand side, and we look at our mole roadmap. Again, we're starting with mass of one substance, ending with a mass of a different substance. We have to take a little trip. We jump in our mole-ville, and we go up to moleville, and it says to put the molar mass in the denominator and 1 mole in the numerator. You supply the specific information, so you put 1 mole of hydrogen equals 2.02 grams of hydrogen. The grams of hydrogen will cancel each other out, leaving you with moles of hydrogen. Now you're ready for your mole exchange. In the balanced chemical equation, for every 3 moles of hydrogen, you will produce 2 moles of ammonia. Just insert the word mole between the 3 and the H and put that in the denominator. Insert the word mole between the 2 and the NH3 and insert that in the numerator. The moles of hydrogen on top and bottom are going to cancel each other. It leaves us with moles of ammonia. Now, moles of ammonia is a good thing to know, but our final answer should be grams of ammonia. So if we look at the mole roadmap, it tells us to get back from moles to grams, we have to put 1 mole in the denominator and the molar mass in the numerator. If you look up the molar mass of nitrogen, it's about 14 times hydrogen, which is about 1 times 3. Then our molar mass of ammonia is somewhere around 17 grams per mole. The moles of ammonia on bottom and the moles of ammonia on top are going to cancel. And we are left with grams of ammonia. It's time to do our math since we have the right unit and the right substance. So we have 5.4 times 1 times 2 times 17 in the numerator, 2.02 times 3 times 1 in the denominator. That should give you 30.3 grams of ammonia. That's our final answer. So what you need to do is practice. If you don't have a practice worksheet, then go on the internet and look up some problems. Go on Khan Academy or something like that and see if you can practice balancing the equation first, then using that mole ratio in a stoichiometry problem. If you have the mass to mass problems that Dr. Kemp gives out to his students, please note for question 2, the unknown is KNO3. You might want to go ahead and label that before you turn this video off. The unknown in question 2 is potassium nitrate. For question 7, it is a totally different kind of problem, a little challenge for you. See if you can figure it out. Thank you for your attention.